Hello guys, today we're going to continue with our inverse kinematics study, and what I will do is I'm going to do a brief recap on the IK of 2 degrees of freedom robots, and we're also going to look into 3 degrees of freedom robots, and also um, after this we're going to look into basically the kinematics of 6-axis robots. In this course, you are not responsible for 6-axis robots, you are only responsible for 2 or at most 3 degrees of freedom robots. All right. Um, okay, so regarding last time, notice that we actually had a small issue when we were doing, if you do cosine pi over 2, right, it actually returns a very small number. And when you uh, basically multiply this by, or when you do some rotations about, uh, if you do rotations, if you apply that basically inside a rotation transformation, it will actually return that. And remember, we actually had a problem if I had, let's say, like a symbolic variable, some set, if I actually do, rotation about z by theta, and then I do, rotation about x by pi over 2, right? And there is an issue here because the pi is actually being evaluated as a floating point value or a floating point number. And this number will actually get multiplied inside this and will actually give us a mess, right? Why? Because of this guy. So turned out that we can actually resolve that by evaluating theta, or the value inside the cosine function, or mainly pi, basically, if you can actually evaluate that as a symbolic value. So what we will do is, so you can do simply that rotation about x by sim of pi and then divide by 2. So this will actually solve this problem. And now we're good here. Basically, this guy will actually be 0, and it will not be a very small number that is being carried inside this operation. Okay, so that is what I want to discuss. The other thing is, let's quickly go back into our discussion last time of the inverse kinematics of 2 degrees of freedom robot. We said the inverse kinematics is what? The inverse kinematics is that given a position or given a Cartesian position of your end effector, find me the position or the joint positions of the robot. And in the case of a 2 degrees of freedom robot, obviously we have theta 1 and theta 2, and xe and ye are provided for you. The first thing that you want to do is you want to look into this, virtual length L, and we know L is going to be equal to square root of xe squared plus ye squared, right? Because this is the x coordinate of the end effector, and then this is the y coordinate of the end effector. Then the first thing that I can do is actually I can find theta 2, right? Before finding theta 1. So I find theta 2, and the way I can do that is I can look into this, right triangle. And I know now L squared, which I already know is also going to be equal to L1 plus L2 cosine theta 2 squared, right? Plus L2 sine theta 2 squared. So with that portion, right? Squared. If you expand this, you will see that you will actually end up with this guy, right? L1 squared plus L2 squared plus 2, L1, L2 cosine theta 2, and I can actually use that to find theta 2. So cosine theta is equal to this by rearranging this and then solving for cosine theta 2. Then I can actually find what theta 2 is by doing the inverse of that. And we know basically the inverse, the cosine of an angle basically is 2 solutions, right? 2 angles, the cosine of 2 angles will give me the same cosine, right? So if theta is like that and theta is actually like that, I will actually get the same value, right? This is my cosine, right? And then this is my sine. So plus theta and then minus theta will actually give me the same cosine. So theta 2 is equal plus or minus this guy. And whatever solution that I actually choose here, I will only choose it only once. So if I choose a positive value, then after we solve for theta 1, it will actually apply also on theta 1. Right? So you have cosine theta 2, or I'm sorry, theta is equal plus minus that. So here, for example, I choose the minus solution, or I could even choose a positive solution. Okay, now let's look into how we can find theta 1. So the way we find theta 1 is, so now we have theta 2 already. We can actually find theta 1 by looking into the difference between these two angles. Beta, right? Beta is the angle that this virtual line makes with the x-axis, and then alpha is the angle that this virtual lines makes with length 1. And theta 1 is nothing but beta minus alpha, right? Now I've already solved theta 2. I can actually find alpha. What is alpha? Tangent alpha is equal to this guy over this guy, right? Opposite over adjacent. What is opposite? I already have theta 2. Opposite is going to be L2 times sine theta 2, and the adjacent is going to be L1 plus L2 cosine theta 2. Okay, and we said you don't want to use alpha is equal to inverse tangent of this guy or a tan. No, you want to use a tan 2. Why? Because a tan 2 will actually tell you on which quadrant you are. If both of the angles are negative, right? if both of the values are kind of negative, yep. Okay, so if you have a value here and then a value here, so basically, right? So if you're here, it will actually not know. It will think you are here, right? Why? Because minus over minus is positive, so it actually return this angle. So you have theta, for example, and then you can actually have also theta plus pi, right? Sometimes your motor is actually theta plus pi is not here. This is a physically different position than theta, right? So if you use 8 and 2, you're good, right? So whatever values you have, if both of them are negative, it will actually return theta plus pi. All right, so now we have alpha. What is beta? So we can simplify beta by this guy, right? So I know tangent beta is equal to ye over xe, right? So again, beta is equal 8 and 2 ye xe, right? And I already have theta 2, right? So I know alpha. Now I can find theta 1 is going to be equal to, let's say, alpha minus beta or alpha minus beta. Beta is here in this case, so or minus alpha. So minus alpha, right, plus beta. Okay, so this is it regarding the IK of 2 degrees of freedom, rotational joints, basically, or 2 degrees of freedom RR robots. Let's look into the 3 degrees of freedom case, and this is what we have. Let me just close this down a little bit. So regarding 3 degrees of freedom robots, is typically it would look like this, right? If it wasn't mainly like, if it didn't have any like linear joints, etc. This is what we're going to be dealing with, and we'll see in the next lecture that the combination of this 3 degrees of freedom robot with a wrist will actually give me the 6-axis robot configuration. But let us actually see how we can actually solve what is theta 1, theta 2, and theta 3 for this robot. And in the case of the inverse kinematics of this robot, essentially what are you providing? You are providing the x, y, and z of your end effector. So you are basically providing the position of that point, and then you are solving for theta 1, theta 2, and theta 3. Okay, let's put that in in more context. What do we have? So this is my theta 1, right? And then these are property H frames. This is my Z0, Z1, and then Z2. And how can I solve theta 1? So here we'll do basic geometry. We'll use geometry to be able to find theta 1, theta 2, and theta 3. So how is theta 1? I know simply that tangent theta 1 is equal to yc over xc, right? So theta 1 is equal to 8 and 2 yc comma xc, right? Now we found that. Second step is we need to find theta 2 and theta 3. If you actually look into this, you will see that this portion of the robot, link 2 and link 3, it is in a sense like a 2 degree of freedom robot that is actually in this frame, right? Okay, so I can actually now find theta 3 and then find theta 2, right? Well, before doing that, let me go to the next slide. Okay, this is the definition of 8 and 2. This is what we did for theta 1, right? 8 and 2, y, and then x, c. We'll start basically by finding theta 3, right? Based on this guy, right? And then we said this guy is exactly look like the one that we actually just solved, right? Use that size a little bit. Okay, here we go. All right, so what is theta 3? Well, I actually have this guy, right? So what is LE initially? So I know LE has to be equal to what? So the coordinate of xc, yc, and zc is provided to me, right? I need to know LE. So LE is actually nothing but xc squared plus yz squared plus zc minus L1 squared. So basically you are kind of transforming this guy into this by removing the distance L1, right? So zc minus L1 will actually give me that distance, right? And now LE is nothing but that guy. And to solve theta 3, basically, I will use exactly what I just did here, right? So I know LE squared has to be equal to what? L2 squared plus L3 cosine, or equal to L2 plus L3 cosine theta 3 squared, right? Which is this guy, plus L3 sine theta 3 squared. So we're good here. We got that. After you expand this, you end up with this guy, and you already know LE, so you can actually solve for cosine theta 3. Okay, now we solved theta 3. Next step is we need to find theta 2. How do I find theta 2? exactly what we did before. We know that theta 2 is equal to beta minus alpha. And I already know alpha. Alpha is going to be equal to 8 and 2, this guy over this guy, which is L3 sine theta 3 divided by L2 plus L3 cosine theta 3. Okay. Final thing is going to be beta. How do you find beta, right? Which is this guy. So you're gonna beta is gonna be equal to this height here, which is ZC minus L1, which is all good, right? Divided by this guy. So what is this length right here? So this length from here to here. So here we're actually in the X1 frame. We're not along X0, we're along X1. And if you see basically beta, right? So beta is gonna be this guy, right? Let me actually throw that. Okay, here we go. So it's going to be this guy, right? Which is a Z of C minus L1, right? How about this guy? What is the length of this guy? This guy is what? Is nothing but XC squared plus or square root of XC squared plus YZ squared, YC squared, right? Okay, let's clear that. Come back here, and then you'll see, okay, so that's it, right? So beta is equal to ZC minus L1 and square root of XC squared plus Y squared. So if you use this, basically now we find theta 2. So basically, simply using geometry, we can find the angles of the 3 degrees of freedom robot that is basically just rotational, rotational, and rotational. Okay, and then we will actually see that we will use this configuration, and then we're going to attach a wrist to it, and then we'll be able to solve the inverse kinematics of 6-axis robots. So in this course, you are not responsible for the inverse kinematics of 6-axis robots. You just need to be basically, you need to understand this very well, basically, and how we actually do the IK of 2 and 3 degrees of freedom robots. And now that I actually have solved for my angles, I can actually use my homogeneous transformations to be able to plot the robot, right? So what is H? So basically now, let me just start this. Okay, now that I actually have theta 1, theta 2, and theta 3, I can do my homogeneous transformations between the various frames. I can do H01. That's going to be what? Rotation about Z by theta 1. So now your X0 is along X1. Then you translate about Z by L1. Then you rotate about x by pi over 2, right? Because, after you do this, so you rotate about z0 by theta, you translate, now your x0 is along x1, right? But your z0 is up, so you still need to rotate about x by pi over 2 to basically put z0 along z1, right? So that is why you need this last transformation. Once you are here, basically, it's nothing but you rotate about z, and then you translate along x, right? So here we rotate about z by theta 2, and then we translate along x by L2. Last one is we rotate about z by theta 3, and then we translate about x by L3. Now that we actually have H01, H12, and then H23, we can actually multiply all of these together, and then I can actually obtain the position of my end effector based on thetas. So now we have the IK and then the FK. So I can literally provide simply X, Y, and then Z. I can calculate my thetas, and then I can actually plot the robot. So this will give me a sense of how I can actually animate an industrial robot, right? So you start with the inverse kinematics. The inverse kinematics will give you the joint positions. Then you use the forward kinematics or the H transformations to be able to actually plot the robot. In MATLAB, this is how it actually looks like. We basically provide the Cartesian point, or what is the tool center point, for example, in this case, XC, YC, ZC, right? I can change those whatever I want to do those. I can also provide the link lenses on the various robot, and then based on these, basically, I'm actually solving whatever theta 1 based exactly on what we just did, right? Theta 1 is provided 8 and 2 YC XC. We've already done that. LE, we solved theta 3 first, and then we actually obtained theta 2. Okay, and you can here obviously change any dimensions in a robot, or you can change where you would like your end effector to be, and based on that, we actually solve all these guys. And after we do those, obviously, like I said, we do the homogeneous transformations, and after the homogeneous transformation, we can actually obtain the origins of the various frames. And then we can plot them, right? We said last time we can plot the link, right, based on the line function in MATLAB, and then we can plot the various points. And by doing so, basically, we can actually plot and then animate the robot and be able to actually visualize how the robot is actually going. We can actually, simulate the robot moving along a straight line, or in X direction, Y direction, or along any line. Basically, you would be able to actually simulate that, because now you have the inverse kinematics model working. All right, guys, so that is it regarding this lecture. In the next lecture, I will actually go over, how we can actually attach a wrist to this guy, and then, to be able to control the orientation of the robot, right? Or the orientation of the vector. This configuration actually will only solve theta 1, 2, 3 at this point, right? And I will not be able to actually control how I'm actually, orienting this vector, right? It will simply go to this point, but we have no mean of actually doing the orientation. If you want to do orientation control, you actually have to add 3 more joints to this, and this is called actually the rest. Any questions on that, guys? Email me, and I'd be very happy to help you out. Okay, bye-bye.